welcome to another WJEC A level physics question. This time it's January 2013's question 5 from the PH4 paper. There's a question on orbits and the wider universe, which is currently in Unit 4. What we've got in this question is a spiral galaxy moving away from the Earth and rotating as shown. So we can see that this spiral galaxy is rotating at 1.4 times 10 to the 5 meters per second. But the centre of mass of this galaxy is moving away from us at 8 times 10 to the 5 meters per second. We've got to calculate the maximum and minimum redshift measured by an Earth observer when light of wavelength 656 nanometers is analysed from this spiral galaxy. So we're going to use delta lambda over lambda is V over C, and hence delta lambda will be V over C times lambda. So to find the maximum redshift, we need the maximum recessional velocity of this of a star, if you like, in this galaxy, which would be a star down here, which will have the two velocities added together. The centre of mass of the galaxy is moving away at 8 times 10 to the 5 meters per second, but the star is also moving relative to the centre of mass of that galaxy at 1.4 times 10 to the 5 meters per second. So our maximum delta lambda is going to be that maximum speed of 9.4 times 10 to the 5, that's the 8 times 10 to the 5 plus the 1.4 times 10 to the 5, over the speed of light, and multiplied by the base wavelength of 656 nanometers. I'm going to leave it in nanometers, I'm just going to remember to give my answer in nanometers. So putting those into the calculator gives us 2.06 nanometers. 3 significant figures is justified because of this wavelength, but you could go with 2 because of the speeds there. For the minimum delta lambda, well, this time this will occur at this position where the star is within its rotation, at least heading towards the Earth, but because the centre of mass of the galaxy is moving away from the centre of the Earth at a bigger speed than the rotational speed, then the net speed away from the Earth for that particular star would be 8 take away 1.4, or 6.6 times 10 to the 5 meters per second. Still 3 times 10 to the 8 on the bottom, still 656 nanometers. And this one gives us 1.44 nanometers. Next, the mass of the spiral galaxy is estimated to be 8 times 10 to the 39 kilograms based on the amount of light that it emits, and we're going to use that figure to calculate the gravitational force exerted on the unit mass at a distance of 1.5 times 10 to the 20 meters. So here we've got a choice of 2 methods really. We can calculate gravitational force with F equals G m1 m2 over r squared, but if we realise that force per unit mass is the definition of gravitational field strength, we can use G equals big G m over r squared. They're both effectively the same thing because of that unit mass. So G is 6.67 times 10 to the minus 11. Mass of the galaxy 8 times 10 to the 39, and the distance 1.5 times 10 to the 20 squared. So putting those into the calculator will give us an answer of 2.37 times 10 to the minus 11 newtons per kilogram. Next we've got to show that for an object in a circular orbit of radius r about a body of mass m, the orbital speed v is given by v equals root gm over r. Well, this is a standard derivation. We start by equating the centripetal force, mv squared over r, to the gravitational force on the mass, g big M little m over r squared. The mass of the object that's orbiting cancels out, and we're left with v squared over r is gm over r squared. We can cancel one of the r's either side. So now we've got v squared equals gm over r, and simply square rooting both sides gives us the required v equals root gm over r. For the last part of the question, we're told that for this galaxy, that maximum rotational speed of 1.4 times 10 to the 5 meters per second was measured at a radius of 1.5 times 10 to the 20 meters. And we've got to use the equation that we've just derived to investigate whether dark matter might exist in this spiral galaxy. There's sort of four things we could do here. We could work out the speed, what it should be given the mass from the previous part of the question, or we could work out the radius of the orbit that would go with that speed for the mass given in the previous part of the question. We could even work out the value for the gravitational constant with the data given and see whether or not it agrees with the standard value. But I think the most logical thing to do here is actually find the mass of this galaxy. So let's start by squaring the equation. So we'd have v squared is gm over r, and hence m is v squared r over g. So let's put in the figures. Mass will be 1.4 times 10 to the 5 squared times 1.5 times 10 to the 20 over 6.67 times 10 to the minus 11. And if we put those figures into the calculator, we end up with a mass of 4.41 times 10 to the 40 kilograms. And that's larger than the value that we were given earlier. The value given earlier was 8 times 10 to the 39. So because the mass of the galaxy is greater than the sort of observed mass from the light emitted, this is evidence that dark matter is present. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye now.